Hello and welcome to van der Waals in action. In this video you will learn about the intricacies of the van der Waals state equation, where it comes from and how to derive it. Physicists are lazy, using idealized models in order to describe the universe. However, such models are often oversimplified and therefore insufficient for complex problems. As we advance our studies into physics, we notice that our approximations are not always reasonable. The simple equations that we have come to know and love must be altered to match our understanding. One common example is the ideal gas equation, a simple equation relating the pressure, volume, and temperature of a gas. However, it relies on the gas being ideal, which comes with a list of assumptions. The three main assumptions include 1. All particles are point masses, 2. There are no interatomic forces between particles, and 3. All collisions between particles are elastic. These assumptions allow for the classic equation PV equals nRT, where P is the pressure of a gas, V is the volume, N the number of moles, R the ideal gas constant, and T the temperature, but this neglects important physical effects pertaining to the nature of the gas molecules. So we need a new gas equation, the van der Waals equation of state. This equation takes two important physical effects into account. 1. Gas particles have a non-negligible volume, and 2. There are interatomic forces between these particles. We will have to make modifications to the ideal gas equation in order to accommodate these effects. Imagine a real gas within a closed box, and let's consider the first modification. Gas molecules do experience interatomic forces. The gas molecules in the cloud will attract each other inwards with van der Waals, reducing the momentum towards the container walls, and therefore decreasing the outwards force against the side of the container. This of course decreases the pressure, force per unit area. We represent this decrease in pressure by equating the real pressure, PR, to the ideal pressure, PI, minus a new term. This new term consists of a constant A related to the strength of the van der Waals interaction, times the molar density squared, i.e. N over V all squared. This gives us the relation PR equals PI minus A times N over V all squared. Now for our second modification. Gas molecules are not point masses and have a real physical volume. This is a pretty simple modification to make. VR equals VI plus a constant. The equation we end up with is VR equals VI plus Bn. In this case, B is a constant related to the size of the molecules, and N is the number of moles in the gas. Now to apply these modifications to the ideal gas equation. Replacing the PI with PR plus A times N over V all squared, and VI with VR minus Bn, our non-ideal gas equation is now as follows. This is the van der Waals state equation, which comes with a lot of interesting consequences. If we rearrange it, for example, we arrive at this cubic equation. If we solve this for V, we would find that there are three values of volume for one value of P. So what's going on? To investigate, we plot P against V for various values of T, giving us lines called isotherms. Generally, an increase in volume leads to a decrease in pressure, which is what happens if you think about it intuitively. However, notice that in the lower isotherms there's a strange section where increasing the volume also increases the pressure. These sections are unphysical and don't agree with real-world experimentation. To make sense of this, we use something called Maxwell area constructions. These consist of drawing straight lines across the anomalous sections, such that the two areas entrapped between the curve and the line are equal. This modification mimics experimental results. Along the straight line, liquid and gas coexist. This is because the liquid is boiling, and the pressure is constant until it has all been converted into gas. There is another important point on the isotherm, the critical point K. This is the mathematical point of inflection on the curve, which occurs only on one isotherm on a P against V graph. At this point, defined by a critical temperature and pressure, or a critical temperature and volume, there is no transition from liquid to gas. Above this point, liquid and gas are indistinguishable. Their joint state is referred to as a supercritical fluid. Let's find the critical volume on a PV graph. To do this, we need to find the point of inflection, where the first and second derivatives of P with regard to V at a constant T are equal to 0. Note that for these following calculations, V sub m equals V over n. This is simply for convenience's sake. First, we rearrange the van der Waals equation of state so that we have P on one side. Differentiating with respect to V twice gives us the first and second derivatives, which we equate to 0. Rearranging them both in terms of RT, we can equate these again and perform some simple algebra to show that V crit equals 3B. To find the critical temperature, we can substitute the critical volume back into our earlier expression for RT, rearrange for T, and solve. We can do pretty much the same to get the critical pressure as well. So now you understand the van der Waals state equation, an essential tool in describing how matter works all throughout the universe. In 1910, van der Waals was awarded the Nobel Prize in Physics for exactly this equation, and it is easy to see why. One of the most accomplished scientists in recent history, who will be remembered as the father of modern molecular physics for eons to come.